Okay, so we should be recording now. All right, so now we're on lecture 19, and by the way, this lecture is so long, I can't just put this into one day. So today's lecture and Thursday will both be lecture 19. So I don't know, you might wonder whatever happened to lecture 16, but lecture 19 is double. So it all works out, I don't know. So anyway, by the way, I did put in a homework that's related to what I'm about to talk with, which is these pulley systems. Okay, so I'm going to show you a little bit about pulley systems. But essentially, what we're going to be doing in today's lecture is some of the heart of statics. Okay, we are going to be doing the heart of statics, which is starting to take and analyze machines. Okay, so now we're not just looking at one piece. We're actually going to be taking a mechanical system apart and starting to look at internal forces. Okay, so that's going to be a little different. But we're going to start it fairly easy, and I think you'll probably see these pulley systems are pretty easy. Okay, so we're going to start by looking at these problems with pulleys, and then we're going to start getting into more advanced mechanical systems. And by advanced, I mean advanced in a statics course. I mean, they're not really that advanced, but you know, we're going to start taking apart the system, and we're going to start looking at forces that are internal to the system. And by the way, later on, we'll actually start looking at forces that are internal to the members. Okay, we'll actually be before this class is over, we'll actually start looking at forces inside of members. Okay, and we'll start, and that'll be a preview for mechanics of materials, which I'm imagining many of you will take in the near future as well. All right, let's get into this. We got here some 3 pulleys, and it says here, determine the force P necessary to lift the 100-pound load in each case. Okay, and so in each case here, there's a force P that's necessary to lift this, and in each case, they're different. So how do we do this? Okay, how do we analyze the forces in a pulley system? Okay, the key thing first is that you want to follow the rope. Okay, because one of the things you got to remember about a pulley system is that the force in a rope is constant throughout the pulley system. Okay, so that's really the key principle. Now, some of you might be doubters of this theory, and some of you might say, well, hold on, I don't know, is it really the force of a rope constant? Well, okay, technically it's not, because there is some friction. But we're going to simplify this, and we're going to say in a simplistic way that the force throughout the rope is constant. Okay, and we call that force typically tension. Okay, ropes, you can't push with a rope, right? You can only pull. Ropes only pull, they don't push. And so that's going to make life simple when we do the free body diagram. Okay, so let's trace the rope. Let's take a look at A. And what I want to do is I want to trace this rope. So if I trace this rope, I'm going to grab onto it here, right? I'm kind of grabbing onto it right here, right? Let me trace this rope. It goes here, it goes around here, goes around there, goes around there, goes around there, around there, and there, right? And as you can see, there's only one predominant rope. Now, of course, there's another rope that actually holds up the 100-pound weight at the bottom, but that doesn't matter. I mean, that doesn't matter that that's a rope down there at the bottom. But as you can see, we're tracing with one rope. And as I said, the force in that rope is going to be constant throughout the whole thing. That's going to be the key concept that's going to enable us to do the free body diagram here. Okay? So, how much force is necessary to do this? Well, I've got to draw a free body diagram. Let me take a look and draw a free body diagram. And really, there's 2 free body diagrams you could draw here. One free body diagram, and I'm trying to box it here, is the bottom part. You could draw a free body diagram of this bottom part like that. But you also could draw a free body diagram if you wanted to of the top part. Okay? You could draw that one as well. Okay? You could draw, and why would there be two different ones? Well, as you can see, that bottom part's kind of connected. You see that there's two pulleys there on the bottom, but they're tied together, right? You see that? Those two pulleys on the bottom are tied together. So really, it's kind of one free body diagram. So I'm going to focus here on the bottom, and I'm going to show you this. Let's do this. I'll keep it like that. And let's draw a free body diagram on the bottom. So I've got a pulley here, and then above it, I've got a smaller pulley, right? Like that, right? And they're connected with some kind of connecting thing, right? Okay? And now I'm going to draw some forces. And remember that the tension in the rope is constant. So this is going to pull up this way. This is going to pull up this way. This is going to pull up this way. And this is going to pull up this way. And they're all going to be with force P, because that's the force I'm pulling through the rope on, is force P. And essentially on that bottom piece, 4 ropes are pulling up. And what's pulling down? Well, the 100-pound force. So you can clearly see now, once you draw the free body diagram of that bottom piece that I have boxed in green there, I mean, you can, once you get the free body diagram, I mean, it's pretty easy to do the rest, right? You just say, oh, well, sum of forces in the y direction is equal to 0 for statics problems. I'm going to say up is positive. What do I have going up? Looks like I have 4p going up minus 100 going down equals 0. P must be 25 pounds. So we would say this pulley system here is basically like a 4-to-1 pulley. Meaning that I only have to pull down 25 pounds in order to lift up 100 pounds. That's pretty cool. I like that. You know, and a pulley system like this could be useful. Okay? I actually can take a force of 25 pounds and lift something that's 100 pounds. Pretty cool. Yeah, a pulley system like that can do that. Okay? You know, obviously, you know, we used to use more pulley systems in places, and we don't use as many as we used to. But, you know, it's still relevant and useful knowledge to know how that works. Okay? Any questions on that? All right, let's take a look at the next one. Let's take a look at B. Now, what's going on there at B? Well, it looks to me like the piece I need to look at is somewhere like this. Right? Okay. And it looks to me like there's really one dominant rope in this, right? The rope attached to P goes around this pulley, goes back up here, around this pulley, and down there, right? So it looks like there's really one rope of this pulley as well, okay? And I'm going to draw a free body diagram of this. Looks like it looks like this. It's got one like that. And if you look at it, the force P is pulling up on this large pulley at the bottom on this side. It's also pulling up on the large pulley on the right side. And because it's wrapped around that other pulley, it's pulling up in the middle. Like that. And of course we have the 100-pound force there. Bless you. I don't know about you, but I know this pollen is getting to me. So, so this is a pretty easy free body diagram as well. Sum of the forces in the y direction equals 0, up being positive. You got 3p minus 100 equals 0. So, okay, that's easy. P in this case is about 33.3 pounds. So that's a 3-to-1 pulley. Okay, so in this case, this pulley system is 3-to-1. I have to pull, in this case, I guess, pull up 33.3 pounds to lift up the 100-pound force. Okay, it's a 3-to-1. So I have a 4-to-1 and I have a 3-to-1. But as you can see, the the pulley system at B is simpler, right? There's only really 2 pulleys. The pulley system at A actually had 4 pulleys. There's 4 different pulleys in order to create the 4-to-1. But at B, it was a 3-to-1 from just 2 pulleys. And then what do we got at C? Well, at C, I have all sorts of things going on. So let's follow this carefully. First thing I want you to do is trace the ropes. Start with the rope you've got the handle on. The handle is right here. Let's trace this rope. Goes around here, goes around here, goes around there, and then it stops right there. But if you look at it, we have another rope. We have another rope here. Goes there, goes around here, goes up there, and goes there. Okay, so in this case, we have 2 ropes. Okay, so we have to be a little more careful with our units and our conventions here. But it's not that hard, right? I think you guys would all agree that these are not very difficult. Just got to keep track of the ropes, keep track of your, what you're doing, right? So take a look at this top pulley. Let's take a look right here. Okay? And let's draw a free body diagram of that pulley right there. I think you can see, because the rope has force P, it's going to pull up here with P. It's also going to pull up here at P. And because it's wrapped around that pulley at the top, it's going to pull up with this P. Now, what's pulling down here is not necessarily 100 pounds anymore, right? Because this is not directly attached to the weight. It's attached to a whole nother rope, right? So we don't know what to call that. So I'm just going to call it R, force R, right? Because I don't know what that is. I'll have to look at the other one, right? So I'll leave it at that. Now, let's draw a free body diagram with the other rope. So each rope basically has its own free body diagram, right? So we have here a free body diagram, and you typically, by the way, focus on the lowest moving pulley. Notice in each one of these, I focused on the lowest moving pulley. And so in this case, I focused on the bottom one there because it's the lowest moving pulley. That's kind of the trick to it. So what happens here? Well, it looks like I've got on this bottom pulley, looks like this is R, right? R here, R there, and R there, right? Because that's the rope R that has force in R is pulling up on each one of those. And on this bottom moving pulley, 100 pounds down, right? So now, how do we figure out the force P such that we can lift this 100-pound force? Well, all you have to do is do the math, and it's not that hard, right? Taking a look at this bottom pulley, we can see here some of the forces in the y direction equals 0, up being positive, right? We got 3R minus 100 pounds equals 0, right? So clearly R is going to be 33.3 pounds. That's the tension in that rope R, but that's not the answer because now we have to look at the top pulley. If we look at the top pulley, right, and we say sum of the forces in the y direction equals 0, up being positive, what do we got? Well, we got 3p up minus r equals 0, right? Well, we know r is, we already solved it, 33.3 pounds. So then we go through there and substitute that in and basically divide it by, again. So basically, P is going to be equal to R divided by 3, which is going to be equal to 11.1 pounds. So this is a 9-to-1 pulley. Okay? It actually gives us 9 times more force. So all of a sudden, if you are strong enough and you can pull with force P maybe 100 pounds, you can lift something that's 900 pounds. Okay? So if you're strong enough, you can lift a lot of weight with this. Okay? Now, this almost feels like you're cheating when you first learn about this 9-to-1 pulley like this. It almost feels like you're cheating because it feels like, wow, I could actually get that much force. Okay? But you are paying a price when you use a pulley system. Okay? You say, well, what price am I paying? Well, if you want, let's say you wanted to lift the front end of a car, right? And let's say you want to lift the front end of the car maybe 10 inches. Okay, you want to lift, you hook this onto the front end of the car, and you figured out that if I can get an 800-pound force at the front end of the car, I can lift it. Okay, well, if you want to do the front end of the car 10 inches, you're going to have to use 90 inches of rope pulling down in order to do that, right? Because even though you get a multiplication of 9 on the force, you get, for every 10 inches that the end goes up, you have to pull down 90 inches of rope, okay? So it takes a lot of rope in order to do this. And the other thing is, you can only go so far with these magnifications with pulley systems because I've assumed there's no friction, but friction can come into play big time, okay? There can be a lot of friction, okay? And so that's another issue, is that it's hard to do these, okay? It's just like gearing, if you've ever worked with any gearing systems, and you'll learn about this in machine design. You can only get gearboxes to do so much of a magnification. You know, your cars have gearboxes, but they don't, what's the highest gear ratio in most cars? Like 6-to-1? I don't know. I mean, not that crazy, right? And so, it's maybe a little bit more than that. But, having a gear ratio like 100-to-1 is really hard to do. Your gears have to be super well, precisely done. And that's hard to do. So typically, even with pulleys, I mean, having a pulley system better than 9-to-1 is really hard to do. As you keep going with pulleys, you have so much friction, it tends to lock it up. Okay? So it can be difficult, right? But I think you all could do this for your homework pretty easily. These problems are usually easy, and usually students are begging for these on the final. They're like, please give me a pulley system on the final, right? You all want that, right? Yeah. So anyways, check your homework. You do have a little bit of this to do, so please go at that, okay? Any questions on the pulleys? You should be able to do those pretty easily. Okay. What I find a lot more interesting are problems like this. Now we're going to start jumping into what I think are some of the most interesting and complex parts of statics. Now we're going to start taking things apart. Now we're going to start really getting into the nitty-gritty and getting down into the details, okay? And we're going to start dealing with mechanical systems, okay, like this one. So this is kind of an odd little system here. Looks like it's some kind of device such that I can maybe raise something up, okay? Some kind of device that's been made so that if I pull 6 pounds in a horizontal direction, I can get some kind of force that can pull this thing up or something like that. Okay, so it says determine the force F given P. Okay, so how the heck are we going to do that? Okay, how in the world? Well, the thing we've got to do here is we've got to start to take this apart. Okay, so when we start getting into these multi-body systems, we have to take them apart, and when we take them apart, we have to be careful how we do it. Okay. All right, so how we're going to do this problem to determine the force F there given P. You could try to do it all as one free body diagram, but the problem really comes into play is that you don't really know what's happening down here. What is that? What kind of connection is that? Well, it's clearly bolted, so that must have all sorts of stuff going on there. That connection to ground probably has reaction moments and reaction forces in multiple directions and would be very difficult to figure out. Okay? So, in this case, we really want to avoid looking at the ground, and we want to take this apart. So, here's what we do. We start drawing free body diagrams of individual pieces. Okay? So, take a look at the handle, for instance. let's draw a free body diagram of the handle. If you look at that system, it's kind of like this. Okay? And what do we got? Well, if you look here, he's going to pull with a force of 6 pounds here, right? And then what else is going on? Well, you've got a point A and a point B. Point A appears to be down here, roughly there, right? And point B appears to be roughly about right there. And they appear to be pinned, don't you? Don't you see? They look like they're pinned to the other structures. And if there's one thing you need to know, you need to remember what we do with pins, right? With pins, you should have a reaction force Bx like this and a reaction force By like this. And with the other pin at A, it's the same thing. You should have a reaction force Ax and a reaction force Ay. Am I missing anything? The only thing you might have a question about is, does this thing have weight? Well, it doesn't say, does it? Right? So, yes, this thing does have weight, I'm sure, but I guess we're going to assume that the weight of each one of these pieces is small enough that we can ignore it. Okay? So we're not given any weights here. I don't know the weight of this handle. So I'm not going to put a weight force in this because I don't know what it is. Okay? I don't even know where it is. Where's the center of mass of this thing? Now, by the way, in a few weeks before the end of the semester, we're going to look at systems and figure out center of mass. Okay? We call that the centroid. Okay? And we're going to do that in this class before we're done. But right now, I don't even know where the weight force would be. Where do you think the center of mass of this handle is? I don't know, somewhere in the middle, right? So I don't know what to do. So I don't have any mass. I don't have any weight. I don't have any information about this. So it must be 0. We'll just assume it's 0. Assume it's small. Basically, we assume it's small relative to the forces. Okay. Now, if this thing were made out of metal, like a iron, steel, it's probably not small relative to a 6-pound force, but we'll just assume it is. Okay. So how many equations and how many unknowns do we have for that handle member? Can I solve for Ax, Ay, Bx, and By in this free body diagram right now? Can I solve for anything, something, nothing? What do you think? Looking at just this, is there a way for me to solve for Ax, Ay, Bx, By directly?
Yeah.
You think so? How so?
Yeah, you can move.
Moments? Yeah?
Yeah.
So which one do we want to do moments about? What point?
A.
A. Okay, let's try it. So if I do sum of the moments about A equals 0, that's cool. Let's try it. I've got here, let's focus on the easy one. The easy one's the 6-pound force. The 6-pound force looks like it creates negative moment about A because it looks like it's clockwise around A. And so the moment is going to be minus 6 pounds times, what's its perpendicular distance to A? Y'all see it? Perpendicular distance from the 6-pound handle force to A. 25 inches, yeah. Okay. Now, what about Bx? Then we got Bx. It looks like it is also a negative moment. If you look at Bx, it looks like Bx, the way I have it drawn, now it's possible I have it drawn incorrectly, right? It is very possible I drew this incorrectly. But that's okay. We'll figure it out later. The Bx looks like it is also clockwise around A. And what's its perpendicular distance from Bx to A? 4 inches, right? And then By, it looks like By, the vertical force at B, looks like it's going counterclockwise around A. So it's going to be plus By. And it turns out, if you look at the picture carefully, the perpendicular distance between B, Y, and A is also 4 inches. You see that? Now, does that equation enable me to solve for Bx or By? No. Right? I can't solve for either one of them. They're both in the equation. So, what else do I do? Well, I certainly could also write this. I could write this. Sum of the forces in the y direction equals 0, up being positive. And I could write, AY plus BY equals 0. Okay. And then I could also write sum of the forces in the x direction equals 0, right being positive. And I'm going to have AX plus BX plus 6 pounds equals 0. Okay, I like it, but I mean, these are all probably useful equations, but I don't see a way to solve for anything at this point. Can I solve for any of those things? AY, BY, AX, BX? I got 3 equations, but I got 4 unknown. I don't think I can solve. Yeah, question?
Yeah, so isn't BC, is that a short link? So
Whoa. Yeah, you're going way ahead of us now. You're fine. No, you're going the right direction. Thank you. Yeah. Yeah, you're right. You're doing the great. Yeah, you're doing great. Yeah. Yeah, BC. Yeah. I wasn't even looking at that. You're ahead of me. But yeah, you're right. So, the point is you can't solve it right now. But let's take a look at BC. Let's draw a free body diagram of BC. Now, here's one thing though. We have to be very careful when we draw the free body diagram of BC. Okay? There's B. There's C. Okay? Here's what you've got to do. Be careful here. Pay attention very carefully. If I can only get you 30 seconds of your attention, make this the 30 seconds of your attention today. Okay? Whenever you write force B in a free body diagram of one piece, notice that this is how I wrote force B on the handle. See how I wrote force B on the handle? Bx to the right, By upwards. When now you're taking those same forces at B and you're putting it onto link BC, you know what you got to do?
Orientate in the same directions.
You have to flip them. You have to reorient them in the opposite directions. Okay? Here's how you have to write Bx and By. You have to do that. If you take the same forces from one piece and put them on another piece, you have to flip the forces. Why? It's as simple as Newton's laws. Okay? It's as simple as Newton's laws. And I always like to use the phrase, if you push on me, I push on you. And I used to do this. I'd have a student come up and I'd say, okay, I put my hand out, and they put their hand out. And I would start pushing their hand, and they would start pushing my hand, right? And I would ask them, I said, what force are you feeling? And they're feeling from me a force at them. And I'd say, well, what force am I feeling? I'm feeling from them a force at me, equal and opposite, right? That's exactly what happens here. If you take the forces at B on one piece and you put them on another piece, you have to flip them. You have to flip them. If you don't do this, you'll get wrong answers. Okay? Now, what about C? Do I have to flip those? No. C is a totally new piece. So I can put C like this. Okay? Now, you are correct. This is a short link. We've already talked about this. But just in case you don't believe me, I can prove it to you very easily. If we take a look at just this free body diagram here of link BC, right? Take a look at link BC. Don't worry about the handle right now. Don't think about anything else. Just think about link BC. And just look at the free body diagram of BC. Don't look at anything else. If you look at just the free body diagram of BC and you say, okay, what if I sum the moments about B equal to 0? Of course I could do that, right? If I say sum of the moments about B equals 0, well, there's only one force that doesn't go through B, right? Because obviously the BX and BY go through B, but also look, CY goes through B, right? There's only one force that doesn't go through B, CX. So you know what that means? CX equals 0. Yeah, CX equals 0. Now, we could also write some of the forces in the X direction equals 0, which would mean minus BX plus CX equals 0. But we know that if CX equals 0, then BX equals 0. Great. So now we've solved for something, haven't we? Now, if that's the case, does that help me go back and solve for the original forces on the handle? Yes. Yeah. So now, and this is the point you were leading to, is now with that information, could I take this BX here and substitute it in there? Heck yeah, right? And now I can solve for BY. Because if BX there is 0, right? If BX is 0, you can take that same equation. I'm going to put an arrow down here so we know. We're going to take that same equation now that BX equals 0. We'll solve for BY. Was there a question? I'm sorry. No? Okay. Thought I heard something. Okay. So BY, if BX equals 0, what's 6 times 25? That's 150? So 150 divided by 4, what's that, 37.5? Yeah. So BY is 37.5 pounds. Okay, so we got that. Now, if BY is 37.5 pounds, then can I use that equation up there to figure out what AY is? Yeah, that's kind of obvious, right? If you look at the second equation I have written there, sum of the forces in the y direction equals 0, AY plus BY equals 0. Well, obviously, if BY is 37.5, AY must be equal to minus 37.5 pounds, right? Now, what does that mean when I write minus 37.5 pounds? That just means what? It's going down, right? I wrote it backwards, right? I wrote, if you look at my free body diagram here, I wrote, I'll put a green arrow on it so we're all looking at the same spot, right? Right there. That just means AY was written the wrong way. AY should have been written down. Now, some of you all might get into this, and I don't want you to do this, but some of you sometimes do this. When you see something written the wrong way, some of you all start to redraw free body diagrams. I don't recommend you do that because it gets you to confusion, right? Don't redraw the free body diagrams. Don't try to fix it because trying to fix it usually leads to more problems. Just go with it.
Because then you'd have to go through and flip all your other.
Yeah, and then you know what you're doing? You're like erasing things and you're rewriting things, and it gets to be like confusion happens a lot. It's easier to just go, you know what I'm going to do is I'm just going to go with AY looking like it is as up, but I'm going to just substitute the negative. Okay? You can do it that way. It's no big deal. There's nothing wrong with that. And by the way, now that BX is equal to 0, we see that in the handle that BX is equal to 0 because we solved it for the short length BC, right? So now that BX is equal to 0, then we can also figure out AX, can't we? Right? Because if you look at the equation here, AX plus BX plus 6 equals 0. So if BX is equal to 0, AX is equal to minus 6, right? None of this helps me solve for what I want to do. Well, it sort of does, but I still haven't solved for what I want to solve for. But AX is minus 6 pounds. Right? That just means that AX is not to the right, like I have it here on my diagram, but it's actually to the left. Don't redraw it. It's not worth it. Okay? So now, what do I got to do to figure out this force F? Well, I got AX, AY, BX, BY, and 6 pounds. I'm analyzed 2 different pieces, but I have to look at one more piece, don't I? I have to look at this piece. Right? I have to look at that bar that goes across. And that bar that goes across is connected to points A and D and F. You see that? So it's kind of, so A, figuring out what happened at A is really important. So I got to draw the bar that goes across. Now, you don't really have to draw things to the exact shape. Typically, you don't have to get too detailed in the shape. I just drew it like this. Yeah, that was not very straight. Let me draw a better straight at least. All right, like that. You do realize that point A is a little bit higher than point D? Sure. So what I did is I have point A like here, and then down here I have point D like this, and then I have the end of the bar. So on the end of the bar here, I have this force F, right, like that. And then I have point D, which is like this. And I'm going to write here dx and dy, right? And then what do I do about ax and ay? Again, don't overthink this. To me, it's easier to do it like what I'm going to show you. I always tell you to flip the forces, don't I? So if I drew ax and ay, look at my handle. Look how I drew ax and ay on the handle up here. I'm going to flip them. On this piece, I'm going to draw AX this way, and I'm going to draw AY this way. That, to me, is the way to go. And then when I substitute in for AX and AY, I'm going to substitute negative numbers. I know it looks a little weird, but that's how I recommend doing it, because you don't have to think about it. You just go, oh, okay, well, I flip it, and I substitute. Now, some of you might, if you flip the original drawing, then you're going to have to flip this drawing, and then you're going to go from a negative to a positive, and you're going to get yourself all screwed up. I think it's easier to just keep it like this. Okay? Now, how in the world am I going to solve for F? Well, I can write one equation right now to solve for F. Do you know what it is? How do I solve? What's the one equation I can use to solve for force F? Some moments about D. Perfect. Yep. Thank you. So if I do the moment about D, and I chose D because I don't know anything about D, so I want to do the moment about D. Good. So if I do this, sum of the moments about D, counterclockwise positive equals 0. Okay? You can clearly see what's the perpendicular distance from F to D. That one's a little tricky. Look at the diagram carefully. What's the perpendicular distance from F to D? F times what distance?
39.
39. Good. 39 inches. Yep. And to me, that looks like a positive moment because it looks like it is counterclockwise. So F times 39 inches. Positive. Okay. Now, AY. Take a look at AY. It looks to me like AY is also a positive moment about D. So here's how I'd write it. I write plus AY times its perpendicular distance. What's the distance across from A across to D? Well, that's just the 9 inches, right? Yeah. AY times 9 inches. Okay. And then finally, AX. It looks like AX is also a positive moment about D because what I'm looking at is this distance here, this perpendicular distance from A here. And I think if you look carefully at the diagram, how much is A above D? If you look carefully at the diagram, it looks like it's 5 inches, right? So that is also positive. So it's going to be plus AX times 5 inches equals 0. Y'all see how I got that? Now, when I substitute for AY, I'm going to substitute minus 37.5 here. When I substitute for AX, I'm going to substitute minus 6 pounds. I think that's the easier way to go. Okay, I think that's the easier way to do it. You might disagree, and that's okay. Do whatever you want. But I think it's the easier way to go. Now, if you substitute both those in, you can directly solve for the force. Okay? If you substitute both in, you can directly solve for the force, which is the answer we wanted. The force is equal to 9.42 pounds. So you can see here there's not really that big of a magnification. There's a little bit of magnification of force. This mechanical device does give me a little more lifting force, but not by a lot. You know, it's not like a huge difference. If I could pull with 60 pounds, it would give me 94. Yeah, that's nice. It's like, you know, like a 1.5, 50% more. Well, that's cool, but nothing huge, right? But this is the first time we've ever done this. We're starting to take apart a mechanical system, okay? And we're starting to figure out all these forces that are occurring at the pins. Usually a lot of pins, but there are forces that are occurring between the members. Okay? Any questions on that? Okay. Can I pause this? Looks like I can. Okay. Hopefully this is working. All right, I want to do one more. And like I said, the next few we'll do on Thursday, next class. In this case, we have some kind of mechanism. I'm not exactly sure what it is. It's some kind of mechanism to hold up that 80-pound force there, the 80-pound mass. Okay. And it says determine the pin forces, the X and Y components, in B, C, and D. Okay. So again, we're looking at internal forces. And so this one is good because it gets you thinking about all the different ways in which you can draw free body diagrams. Okay? Because there's a lot of different ways I could look at this problem. And there's many different free body diagrams I could draw. And so we have to think about what we can solve. So the first thing I would probably do if I were looking at this problem is try to draw a free body diagram of the whole system. This is just like what we did before with the trusses, right? What if I drew a free body diagram of the entire system? So it looks like this. I'd have this, 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 right? And then that's pretty much it. I would have an 80-pound force here. I would have dx, dy there. And then I would have cx and cy there. Now, some of you are going to say, well, hold on a second here. You just drew a free body diagram like that, but you didn't draw what's happening. Like, isn't there a force here? Right? Some of you are going to say, isn't there a force there? Yeah, you're right. But there's also a force here from that same rope, right? There's a rope that goes around, right? And drops down to that 80-pound force. That's basically internal. I'm going to say that that's basically internal to the system. I can draw a free body diagram of just that because the rope force that's pulling either way is internal. And really, the only external forces on this thing are the 80 pounds and the forces at C and D. Because that rope, yes, it is attached, but then it comes down, and those two forces would just be internal. I can draw it like this. Okay? Now, if I do that, and that's totally fine, you can totally do that. I don't think I can solve for everything, but I may be able to solve for some things, right? Because watch this. What if I did this? What if I said, using this free body diagram right here, some of the moments about D equals 0. If I said some of the moments about D equals 0, what are the two forces that create moment about D? CX and the 80 pounds, right? Yeah. So looks like I've got an 80-pound force. Now, what's that perpendicular distance to D? Ooh, that could be a trick. Don't goof this one. What's the perpendicular distance between the 80-pound force, which is all the way out here? What's this distance all the way across to D? 15.5. Yeah. 15.5 feet. Good. And then the only other force that creates moment about D is CX. And that looks to me like CX is 3 feet away, right? And the way I have it drawn, it's a positive. Right, like that. They're both positive moments. That means one of them must be wrong. The CX has obviously got to be negative. In fact, if you go ahead and solve for CX right here, you're going to see it's minus 413 pounds. That's okay. It's okay you got a negative. No big deal. That's no big deal, right? That just means I drew it wrong. That's all. Now, by the way, that means we also can solve for dx, right? Some of the forces in the x direction equals 0, right? Being positive. That looks like dx plus cx equals 0, right? Is there anything else in the x direction in the free body diagram I drew? No, right? So therefore, dx is equal to 413 pounds. I drew dx correctly. Good. Can I solve for cy or dy? Not really. I don't see a way I can solve for cy or dy. Now, the only thing I could do, you might see this and say, well, what about sum of forces in the y direction equals 0? Yeah, that's true, right? So what does that mean? You got cy plus dy minus, don't forget about the 80 pounds, equals 0, right? But does that mean I can solve for cy or dy? No, I can't solve for cy or dy, right? You all see that? So even though I could solve for cx and dx, I can't solve for cy or dy. I know combined they add to 80, but I don't know what they are. Now, so there's a bunch of different ways I can draw this, okay? There's a bunch of different ways I can draw this. So I'll just draw, let's draw this piece here. I mean, you could do this lots of ways. I'm going to draw this piece here that I'm going to highlight in green. Let's take it apart and draw that piece, okay? Just the piece from B to D, that like member there, okay? Okay, so we got this. Goes here. Goes there. Okay, like that. All right. Now, point B is down here. I haven't drawn it yet, so I'm going to do a BX and a BY. But don't forget, now that I've isolated just that one top bracket, I do have to draw the rope force here. Oops. That's 80 pounds. Y'all see that rope there? That's attached to that bracket, right? It's attached to that bracket. I overemphasize how far it is from point B. This distance is not very far, right? That distance, if you look at the picture, has to be only a half a foot. I kind of overemphasized it in the picture. I made it bigger distance. But that distance is only a half a foot, right? From the rope down to B. Okay, what about dx and dy then? How do I draw those? Well, you have to draw them opposite. Or do I not? No, they're really the same thing, right? It's the same piece. It's the same piece, right? Yeah, it's the same piece. So you don't have to draw them opposite. It's the same. It's the same point. Okay, you're not drawing it on a different member. You're still drawing it on the same one, right? So be careful. You don't have to draw them opposite. You've got the dx, which, by the way, you already know this is 413 pounds, and you've got the dy. Now, given this free body diagram, the free body, and I don't think there's anything else, right? I think that's it. So given this free body diagram of this bracket, B to D, is there anything I can solve for now? Yeah, I think I can solve for lots of things, right? So what's the way I solve, for instance, dy? What's the easiest way to solve for dy? Everybody should be able to do this. Say if I gave you this and said solve for dy, within 30 seconds you should be able to come up with an equation that does this.
Put a moment on B.
B, yeah. Put a moment on B. Exactly. Some of the moments about B equals 0. Right? Okay. So what creates moment about B? Well, three things. Three things create moment about B. The two forces at D and the 80 pounds. Right? So let's do the 80 pounds. Looks like the 80 pounds is a positive moment because it's counterclockwise. So it's going to be, oops, well, let's do it this way. 80 pounds times its perpendicular distance to B. Well, we already wrote that in purple over there. That's a half a foot. 0.5 feet. And that's going to be positive. What else is there? dy. dy times its perpendicular distance to B. What's the perpendicular distance from dy to B? Basically, what's the horizontal distance from B over to D horizontally? 9 feet, right? And looks to me that that's also positive. And then finally, the 413-pound force, which is dx. I mean, I could have wrote dx, but it's whatever. You could write dx and substitute 413. That looks like it's negative. So it's going to be minus 413 pounds times its perpendicular distance. The vertical distance from B up to D looks like that's 3 feet. Equals 0. So, boom, you can solve for dy. Turns out dy is equal to 133 pounds. Good. So we got another one. Okay. We need basically 6 pieces of information, and we already got 3. We got cx, dx, and dy. By the way, now that we've got dy, I can go back and get cy, right? So you have to do this. You have to go back to your original equation sometimes. Okay, I got dy is 133. I wrote an equation right here at the top. Now I know this is 133 pounds. Right? So now I can go back and write for cy. Turns out cy, if you solve this, is minus 53 pounds. That just means I wrote it backwards. No big deal. Okay. So I got cx, cy, dx, and dy. That's great. I'm almost there. I guess I could get the rest of it now. All I have to do is analyze that one part, right? I didn't even have to do anything else. I could do bx and by by doing some forces, right? I could write this. Some of the forces in the x direction. I'm looking at this part right here, the bended part, equals 0. What do I got? I got bx plus 413 minus 80 equals 0, right? I think that's it. 413 minus 80 bx. Yeah, those are all the x direction forces. So good. I can solve for bx. Turns out it's minus 333 pounds. So it just means I had it in the wrong direction. No big deal. And finally, I can write out this one. Some of the forces in the y direction equals 0. Up being positive. Good. And that's going to be by plus dy. That's it, right? Equals 0. So by is just minus 133, because if dy is 133, by is equal to minus 133 pounds. So now I got all the answers. All I had to do was analyze two different pieces. That's not the only free body diagrams you could draw here, though, okay? You could have drawn other free body diagrams. For instance, you could have drawn the bottom piece, too, okay? You could have drawn A, B, C. In fact, I could have asked you for the pin forces at A as well. I didn't. But what if I said, what's going on at the pin at A? I could have asked you for that, okay? What I could have done at A is I could have said, okay, you've got this thing here all the way across. A, you got point B, and you got point C. And we could have written it like this and said, you know what? I could have started with this and said, okay, I'm going to write this as CX, CY, BX, BY. And then I don't know what's going on A, but I could have also wrote AX, AY. And if I would have asked you for, if I would have given you CY and BY, I could have done AY. Notice I haven't even put the pulley in there. I could have also redrawn A with the pulley. I could have instead said, you know what, I'm not going to look at point A this way. I'll draw it with the pulley and have the pulley around it, right? I could have drawn it that way, and then I would have had to put forces on the pulley. I would have had to put a force. I'm going to put these forces in different colors to differentiate. I would have had to put a force like this and a force like this. So it just depends on how you look at it, okay? The thing I want you to see here is there's lots of different ways to solve these, okay? There's not going to be one solution path, all right? There's not just going to be one way to go about this. You could look at it. It depends on how you want to draw the free body diagram. There's nothing wrong with drawing a free body diagram. If you take a look at this thing, there's nothing wrong with drawing ABC, the link ABC across. You could either include the pulley or not include the pulley, okay? You could draw it like I did originally and not include the pulley, or you could have drawn the pulley as well. It does change the analysis, right? Because here's the deal. If you included the pulley here, the forces at the pin at A become internal and don't even matter. If you don't include the pulley, then the forces at A, you have to put in as AX and AY. So it depends on which way you draw it. Do you include the pulley or not? It doesn't matter, really. You just have to figure things out. So if you include the pulley, then now all of a sudden you have, instead of having unknown internal forces, you'd have an 80-pound force like this and an 80-pound force like that. That might be easier. In fact, had we figured some things out here, we could have said, you know what? I don't want to include the pulley. Oops. I don't want to include the pulley. I want to include the pulley and have it like this. And now, if I would have some moments about point B, right? If I were some moments about point B, could I figure out CY? Sure. If I some moments about point C, could I figure out BY? Sure. Right? See, there's different ways to do this. There's not just one way. You could draw it like that and include the pulley in this free body diagram, or you could have just said, no, I'll just draw it as a pin at A. Either way is fine. Okay? Either way is fine. All right? So you can do it either way and then figure things out. But I will tell you, some ways make it easier than others. Okay? Some ways make it easier than others. All right? Any questions on that? Okay. So what I'm going to give you in your homework is going to be some of these. We're going to start taking these apart, right? And next time what we're going to do is we're going to look at this a little deeper, okay? We're going to take apart some harder ones. Sometimes, I will tell you this, there are some mechanical systems where if you don't draw the right free body diagram, you get stuck. And that's what's going to happen next time. You get stuck. And you're like, I can't solve this. Well, it's because you didn't write the right free body diagram. What you did was correct. There was nothing wrong with what you did. You just didn't write the right free body. So what does that mean? Does that mean that's bad? No, you just have to draw it differently. Rethink it. And if you rethink it, maybe you can see a different way of solving the problem. Okay? That's frustrating for students because a lot of students like to do A to B to C. But sometimes you do A to B to C, and then you got to back up and redo B because you got to draw it differently. You got to rethink it. Okay? So it's not so easy all the time. We'll show you next time. All right? Okay. Let's see if this works.